Hello. Is there anybody in the chat who can confirm that I'm alive for me, please? This always happens every class. My internet's got to let me know that it's not willing to do this. All right, thank you. So I'll backtrack here a little bit. I had said that the last assignment, it might be kind of a big one, so if it's a big one, then I'll be giving you until like that Saturday of after finals, you know. I need at least a few days to grade it before grades are due. I also need to MOS it with all of the other sections, so I won't be able to give you like as much time as you may wish, but at least it will be maybe 2 weeks, maybe a week and a half, depending. So I'll take a look at that and I'll get it going here pretty soon, just so you guys can be prepared. And hooray, it's the last assignment. I'm sure you guys are happy about that. It looks like most everyone who is still participating in our class got to turn in the assignment. So I'm happy about that. I know quite a few of you got it figured out. So that also makes me happy. So I'll get that graded sometime in the next week and give that back to you guys. And that's pretty much it, I say, for announcements. So I guess we'll just kind of hop back in here. I do just want to check our notes on linked lists to see if there's anything that I missed. Maybe we can throw in a little bit of doubly linked list stuff that might appear on the test just in case. So I'm going to double check that real quick. But here we have our doubly linked list image from last class. And so today we're just going to code up the two functions. One is going to be the insert function, which will insert nodes in a sorted order always. So the list will always be sorted and we'll never have to call a sorting function. So we're going to be doing that function, and we're also going to be doing a delete function, just so you can see it, right? And so on the test, I probably won't ask you to write, an insert a node to a sorted linked list problem, but I may ask you to delete a node from a linked list kind of thing. So we are going to cover that. So where are we here? Let me check. Got some notes. Yeah, so overall I think we've pretty much covered just the basics of it. There are a few things that I want to add. These are kind of some good test questions. And let me ask for some class participation here while we do this. So inserting a node to an SLL and inserting a node to a DLL. Swapping nodes and swapping nodes so I want to ask you is I'll kind of do these swapping nodes with you, these ones down here, because there's quite a few answers to these, but what I'm going to ask you is how many pointers do we need to update? These numbers are always good to remember. And so for an SLL, let's see if I can find a nice picture here. For an SLL, if we happen to be inserting a node to this list, anywhere, how many pointers do you think that we're going to need to update, just in total? Three. T. Peter says 3. So let's talk about that. So let's say we're putting a node here between 1 and 2. We'll definitely have to update number 1's next pointer. And we're definitely going to need to update the new node's next pointer. And I think that is really it. Or if we're inserting at the beginning of the list, then we're going to need to update the head and the new nodes next. And if we're inserting at the end, we're going to need to update this next and the new node next. Now, if we even just come here into this code and look, let me see if I updated the SLL, which I should have. If we check just a few of the insert functions, maybe I can prove myself wrong. So in the tail, this is our tail insert. It looks like this could be considered 1. This could be considered 1 pointer update. And then this one could also be considered number 2. I think. And this is going to be at the tail, right? So those are our 2 inserts there. And then did I do a head insert as well? I assume I did. In which here is the first pointer update where we update the new elements next. And then we update the head to look at the new element. So that's 1 and 2. So that's 2 pointer updates in general. So if we're going to do the DLL, then what do you think that looks like? Let's kind of look at here. So we can insert here at the head. We could insert between these nodes, and we could insert at the end. So if you just want to take a guess at all, we'll see how we did. Red Rose says 4, and I like the sound of that. It's the last one times 2, right? So let's say we're inserting between these 2 nodes here. We're going to have to update this node, its next pointer. We're going to have to update this node's previous pointer. And then the new node, we're going to have to update its next and previous. So we'll keep that in mind when we're doing our insert function for today's DLL. Now, if we consider the head, then we're going to have to update this thing's previous. We're going to have to update the head, and we're going to have to update the new node's 2 previous and next pointers. Similar here at the end. So I think that's completely right. So for the most part, I'll put these on our test review, but these will probably be test questions for linked lists. Now these kind of get kind of nasty, right? Because we already talked about that, so I won't spend too much time on it. We actually have a note here, right? So if we're doing an easy swap, we're going to update at most 3 pointers, and if we're doing a hard swap, we're going to update at most 4 pointers. So we can just kind of put that in there. And so if we're going to swap nodes in a DLL, let's think about what that might look like here. And then I'm actually going to take a screenshot so I could kind of, count what's going on here, because I'm interested in doing that. So let's say that we're going to swap this node here. It's kind of hard to see, but I've highlighted in the yellow. And we're going to swap this node here. So they're not going to be adjacent nodes. And so if we're going to swap them, we're definitely going to have to update this guy's next. We're going to have to update this previous one, right? Because kind of this one's going to look over here. And this one is now going to look at this one. It's going to be kind of hard for me to do that. And then this one, we're going to definitely have to update its next. We're going to have to update this one's previous. We're going to have to update this one's previous. And we're going to have to update this one's next. So what is that 6? Did I get everything? Oh, hold on one second. We're also going to have to update this one's previous. And let's just see if we got it all. That's 7 of them, right? Did I miss any of them? I know that this is probably not good note-taking, and it's kind of hard to see. But I just want us to be aware of all of these pointer updates that we have to make. Oh, and we're going to have to update the head, right? So that's 1, 2, 3, 4. So I think it's going to be safe to say that it's kind of times 2, right? So we did just count 8 pointers there. And I bet if the nodes are adjacent, we're only going to have to update only 6. So let's look at that real quick. So let's say we're just going to update these guys. Yeah. I think that's a good guess, Red Rose, but I'm thinking that it might be 6. So let's just take a look. So let's say we're swapping the adjacent nodes. This is definitely going to need an update, and this one's definitely going to need an update. Now this one is going to get swapped. Yeah, so this one needs an update as well, and so does this one. And this one needs an update, and this one will need an update. But other than that, I don't think there's anything outside of that because there's no nodes in between. Did I lose my stream again? I don't think I did. I think we're still connected here. For some reason, my my moderation screen went dead there for a second. T. Peter's got a good question there, so let me just throw this in here. It's going to be 6 or 4 pointers, or 8 pointers, right? So that's kind of nice. 3 times 2 is 6, and 4 times 2 is 8. So it's just some things to keep in mind when we're comprehending our linked lists. So we'll kind of move on here finally to our coding so we can get that done and out of the way and move on. But first, T. Peter asks, would it not be easier for smaller linked lists to create a new linked list in the updated order you want? Now, so first off, for those of you who maybe got that on the homework, that's kind of what I was implying for that last question there where I had asked, is there any way that we can sort a list without using, I think, bubble sort or swapping function? And so maybe you came up with a different valid answer, which I'll be sure to check for. But what I was implying was that you could just take an empty linked list and a new linked list and just insert the nodes in a sorted order to the empty linked list, one by one. And that could be considered a way to sort a list. And so T. Peter asks, is it easier for smaller linked lists? And I say perhaps, you know. I think when we consider the term easier, there's kind of 2 sides to it. The amount of code required for it. I think that the amount of code required to swap nodes and sort them using for loops is quite a bit, right? So if we just kind of had to, you know, pull off a node and insert it into a new one, I think the amount of code for that would be considered easier. In terms of computer processing, I think it could be up in the air. As I described before, when we use these bracket operators, right, where we're looping through the list over and over and over again, just to get some bracket at an index, I think, sure, it could be more efficient. But I'm sure there are sorting methods out there for linked lists that could be considered easier, at least on the computer processing, than the method you suggest. But yes, I'll give you a good yes for that. In general, smaller lists, you don't need super efficient sorting algorithms for. So let's get started here on our inserts. What is this? This is the SLL, huh? All right, here we go. So let's kind of put some comments down, see what we're going to do. You're welcome. We are going to insert nodes in a sorted order. You're going to insert nodes in a sorted order. It's probably going to be good for us to have a paint out just in case we need it. So I can maybe give some... Woo! So I can maybe give some values to these guys. So let's go ahead and do that. I think we're working with ints today. So maybe in this data here, we can have a 2. In this data here, we can have a 5. In this data here, we can have maybe a 27. And down here, we can have maybe a 32. All right, so we've got some integer elements in our list. And so let's consider a few cases. All right, because if we're going to be inserting a node, it could appear almost anywhere. Let me give this a nice fill. So it could show up here, right? It could show up here, meaning that the new element will be less than this element. So that's kind of our first case, right? So let me kind of write these down as we think about it. So case 1, the inserted item is less than the head node. Case 2 and case 3. I'm going to ask you guys to take a guess on what the case 3 is, but first I'll give you case 2. Case 2 is if the element is going to be between 2 and 5, or it's going to be between 5 and 27. So it's going to be appearing between any of these nodes here, right? So that's going to be case 2. It's between 2 nodes. And so with that knowledge, what do you guys think our case 3 might be? Case 3 is the end. Yeah, that's exactly right. That's exactly right. And so there's a few things that we have to consider. We don't need to look at that anymore. Let me kind of scroll here. Case 3 is it's down here at the end, right? In which it's still not between, any nodes, right? So it's actually at the end. And so we have to consider what kind of pointers we're updating for these inserts, right? If we happen to be inserting here, it looks like we're going to update maybe 4 total pointers, right? Let's see what I said in the notes here. 4 pointers, right? And probably 4 here at the end and 4 at the head, but what are they going to be? Some of them are going to be null pointers, and some of them aren't going to be. So we actually have to kind of look for these things in our insert to make sure we don't have many problems. So case 3. So the first thing that I like to do is always to make a new node, right? This is an insert, so let's just call our new right up front, so we don't have to worry about it. So just as always with every linked list, the first step is to allocate something. So we're going to have our new element here is equal to a new node. And inside that new element, let's go ahead and insert our item, right? Now, as always, I like to prepare the... Sorry. I messed that up. Getting excited here about these linked lists. The data, right? We got to put the item inside of the element. That's what I meant to say. And the next, I like to prepare it for the end, as always, right? We're preparing this just in case. You know, what if the list is empty, right? That's also kind of a case. I'll put case 0, right? Empty, right? So if the list is empty, then we'll hit this case. If the list has one element in it, it's either going to be case 1 or it's going to be case 3, right? In which it's greater than the, it's less than the head node, or it's greater than the head node. And then if the list has 2 or more elements, it's either going to hit case 1, case 2, or case 3. Okay, so it's good that we plan this out and make sure that we're keeping an eye on what could happen here. So now that we have our new element, I also want to do this. This is a doubly linked list, right? So let's make sure that our previous pointer is also initialized, just in case, right? Just in case. So now let's kind of look for our cases. Why not? We'll just go one by one. So our first case is the list is empty, right? So either or of these could work, right? If we check to see if our head is equal to null pointer. Or I like to do and here because it should always be the same. Like I said, you don't actually need this and, but I'm just trying to let you know that you guys have options here, right? Because there's kind of two indicators to an empty linked list. And I'm saying both of these should be true. Both of these should be true at the same time. So you can either do one or the other, but, you know, why not both? And so if this is the case, then we can just say that the head is equal to our new element, right? And maybe we do a nice size plus plus here. And then we return. So let's kind of put that here. This is our case 0. Handled, right? That's the easiest case. We really didn't do much there. So now let's continue in our broken down problem here, and let's move on to case 1. Excuse me, I had a little voice crack there. And so as I said, if the list has one element, it's either going to hit case 1 or case 3. And if the list has 2 or more, it's going to have the chance to hit all of these. Okay, so I'm actually not going to do any if statement here. I'm just going to continue on as normal. Meaning, you know, I'm not going to say if size equals 1, though you could. We're always just going to check the head now to see if that item is less than whatever's in the head. So we could do this, right? I mean, of course there'll be an if statement here. I'm just talking too much is what I'm doing. I'm overthinking. So if our head data happens to be greater than the new element data, this is going to be case 1. And so there's a few things that we have to do here. We have to do 4 total pointer updates, right? In case 2, we only have to do 2 pointers. And those happen right there, right up top, right there. But now we have to update 4 total pointers. Does anyone have any ideas what these pointers are? Now, here, I'll make it easy on you guys. Obviously, the 2 pointers inside the new element. That's always 2 of them. What are the other 2 pointers? Let's see. T. Peter asks, does head equal null pointer, does that check next and previous in a DLL? No, it doesn't. Maybe we can kind of help you understand what's going on. Whoops. That was just MOBA. So if we have no nodes, then we don't have a previous or a next. So if head is equal to null pointer, then we have no data that's been allocated at all. And so there is no data, there is no previous, and there is no next. Does that answer your question at all? And if not, could you maybe rephrase it a little bit so that I can help you better? There's going to be 4 pointer updates in here. Alright, so we're going to have these 4 pointer updates, right? So the 2 that are in the element, we're also going to have to update the head. Let's kind of put them in a comment here, right? Update the head, we're going to need to do that. We're going to need to update the head previous, and then we're going to need the new element pointers as well. That's 2 of them. Oh, Red Rose said, right, head is the pointer to the first element of the list. It's stored outside the struct and in the class. Oh! Yeah, so this is kind of new, right? So I want you guys to know that this program would work like this as well. This might be good to kind of talk about. This could work. You know, we could just have node as a type that can be accessed anywhere. But when we wrap this thing inside of a class, it prevents people from just declaring nodes. And the best part about this sorted DLL is that the node inherently is a little bit dangerous when it comes to memory, right? We've got 2 pointers sitting in here, and we've got a pointer sitting in here too. And so we're kind of messing with memory, and it's causing some problems, right? So this is, excuse me, this is just a class, right? This is just a struct, and it's private, right? So actually no one has access to this stuff except for the DLL. And by the time someone comes down here into main, and declares a sorted DLL, you know, DLL, the only thing that they can do is call clear the list. They can delete, they can get some data, they can insert, they can call this equals operator, and I guess they could call the destructor. But the person in main has no access to any of the dangerous parts of the class, right? So that's why classes are so beautiful to begin with, is that we can kind of wrap up all the dangerous things in the private section here. And so that's exactly what we did. We just declared a data type inside of the class. Thank you for pointing that out, Red Rose. So let's continue on with this one. So if this is the case, we're going to have to update 4 pointers, right? So let's go ahead and do that. So let's start with the new element. So the new element next is definitely going to be looking at the head, right? That's definitely something that will happen. And the new element previous will be looking at null pointer. Now look, I kind of prepared this just in case, right? So we already did this. We already did this up here. So that handles the update number 2. And so the next one that we're going to say is, hey, the head previous is now equal to the new element, right? That's our third pointer update. Give me one moment here, please. And then lastly, we're going to update the head, right? So now the head is equal to the new element. And that's number 4. That's number 4. And that's it, really. So maybe I'll do a size plus. I'm not sure if I'm going to... You see, here I'm checking for the size. So I didn't want to update it yet, but maybe I'll just do this now, because I don't think I'm going to be checking for the size anymore. So I'll kind of just pull that out here, and then I won't have to worry about it in here. And in this case, I'll just return. Then maybe we can do an else statement here. In fact, if we do the else statement, we don't even need the return. And down here, we'll just put the return. So now, it's our job to handle the next 2 cases, right? So we handled case 0 and 1. So now we have to do case 2 and 3. Now I'm going to do this in a loop. And so if we're looking at this, there's going to be kind of 2 cases, right? The case that it's going to be between these 2 nodes, or it's going to be at the end. And so I would actually like to keep 2 traversal nodes. Now this could definitely be done with 1 traversal node because you have access to that previous element, right? If you recall last week or 2 weeks ago, when we talked about swapping elements, things got a little confusing when we had to traverse through the list multiple times to find, which node is previous to the leftmost node. If we happen to keep 2 traversal nodes here, we kind of resolve that problem, right? So I could have done that previously. But also, since this is a doubly linked list, we've already kind of resolved that problem because we have this pointer here. But to kind of give you an idea, you see this pretty commonly in the C++ literature. There will be two traversal nodes, and one will be called current, and the other one will be called next. So let's go ahead and do it this way. So let's make some traversals. And this one's going to be our current node. And I want that to be equal to the head. And I would like the node next node to be equal to the head next. So these are our traversals. And sometimes you might be, you'll also hear about previous and cur. So this one might be the previous node, and this one might be the current node. Kind of depends on where you're looking. But I kind of like to keep it like this. This is how it works in my head. So now we're going to kind of begin looping through this list. Now I'm wondering to myself, how many times do we have to loop? Probably size, until something is equal to null pointer. But the truth is, I kind of think that I don't want to think about that too hard right now. So what happens if we just do this for fun? I know I've said this before, especially at the beginning of the semester. If I really don't know what my loop is going to look like, maybe I'll just do a while true. And then I can later break out of this loop with an if statement if I'd like. So we're going to begin with that. And so now let's begin our checks, right? So there's kind of there's a few things that we need to check for here. We need to do both the cases, case 3 and 2, right? Can anyone tell me what's wrong with this? If I just did this, if I said, all right, I'm ready to do my check. So I'm going to do a between statement here, right? So if the current node data is less than the new element data, I'm going to kind of break this out here a little bit. I'm going to go down onto the next line. So if the current node is less than the new element, but if the next node is greater than the new element, then we have found, here, let me do this. It's looking a little gross. This is our case 2, right? Can anyone tell me what is wrong with this? Now, don't get me wrong, we will definitely have to make this check at some point, but we're missing something that's very crucial here, and it will cause a problem in our program. Many of you guys experienced this problem this weekend while doing the assignment. And so if you have a guess, let me know. But I'll only give you a few seconds so we don't end up waiting here all day. Loaf has come to say hello to everybody. Maybe she can say hi. And then she's got to move on. She's looking for the water, which I put on the ground. There you go. CBA, yeah, CBA, you kind of got it, right? If it reaches a null pointer. The real answer here is if it does reach a null pointer, this program will segfault. So I would say that current node is guaranteed to have some data, right? Because notice up here we checked first if the head was equal to the null pointer, and it's not. And then we also already checked to see, you know, if the new element could be less than it, and it wasn't. And so now we know for sure that this head contains some address. But what we don't know is this. Like, as I said at the beginning, we have to look at these cases, right? If this list is only one element in size, there's a case 1 and case 3, right? The inserted item is at the end. And so if it's a list of size 1, this next node, guess what? It's equal to null pointer. And guess what I do here? I dereference it. And what happens when we dereference a null pointer? Segfault. All right, we all know this, hopefully. So we can't check for our case 2 yet, right? You know, if we want to stick an order here, we can go ahead and do that. So how's this? This is how we fix this. This is how we keep things nice and clean. We're just going to nest this inside of another if statement, and we're going to say, hey, I like to be extra safe, right? So is that fair? Say, hey, as long as both of these nodes are something, right? We're not at the end. This is basically what this says. This basically says, if we are not at the end of the list. That's what it says. Then we can do our check here, and if it happens, then we'll go ahead and do our insert and we'll return. So let's go ahead and handle that. So 4 pointer updates, excuse me. And this one's pretty easy. So the current node, next, is going to be equal to the new element. The next node, previous, is going to be equal to the new element. Right, that's number 1. This is number 2. And then we've got 2 more, right? Null pointer will not do it in this case. So the new element next is equal to the next node. That's number 3. And the new element previous is equal to the current node. That's number 4. That's a return. Let's get out of here. We don't even have to do that if we don't want to. We can just break it. We'll break out of this while loop, and then we'll hit this return down here. So there you have it. That's case 2. If there are any questions about that, got to make sure that we're not at the end of the list, and then we can go ahead and safely dereference these. And then we'll do our 4 pointer updates, and then we'll move on. Now let's do a few else ifs, right? I'm going to do a little bit of error checking in here. So I'm going to say else if this, if current node does not equal null pointer and next node does equal null pointer. Okay, so this means we are at the end of the list. So this one is pretty easy, okay? And let me just show it to you. If our new element, let me go ahead and put something in here. Well, I can't. So let's pretend that this is 30. Let's pretend that this is 30. If it was 30, it would have been caught here in our first check. It would say, hey, this is less than this node. So it's going to go here. It's going to go right in the middle. But let's say this is 33. It will have skipped over these two, and it will have reached this point. At this point, we know it's at the end. So in fact, we don't have to check. We don't have to check to see if it's less than 32, you know, to know if it goes in front or in the back. We know it goes in the back. Okay, that's a given. We're at the end of the list. New element is the end. Okay, so this one's pretty easy. Looks like we've got 4 pointer updates again, right? Let's go ahead and do those. So in fact, the current node next is equal to the next node, which is equal to null pointer, so we got to update that. You say, hey, current node next, you are now equal to the new element. And we got to say, hey, the new element, your previous, is now equal to the current node. Let's kind of start counting here. That's number 1. That's number 2. maybe there's only 3 updates that we need to make. Maybe I made a mistake here. Let's go back and take a look, huh? So if we put it here, the next needs to get updated, the previous... Yeah, maybe there's only 3. Let's put that in the notes. Make sure. Right, because the next one that we would need to do is new element next is equal to null pointer. But guess what? I already did that. Do it. Prepare, just in case. I said let's prepare that one just in case. Which we did, okay? So number 3 was already taken care of. Okay? So maybe there's only 3 pointer updates for that one. And if that's the case, then we'll just break out and we're done. And I'll do a final else statement, right? A final else statement. This else statement is not required in any way. Just gonna say cout. What? Now, in real life, you might say current node and next node equal null pointer. Why did this happen? Or somehow current node is equal to null pointer and next node does not equal null pointer. And either way, something weird happened here, so let's just get out. And maybe when you're a professional someday, you will put a better error statement there, right? I'm just going to say what? And just say this death should not happen. Okay? So I think that's good. I think that's it for our insert statement. How many lines is that? 67, including comments, all the way to 121. It's like 30-some lines right there. That doesn't sound easy at all, does it? But I promise, we did some planning, right? We did some planning. Planning will always help you in computer science. Think about what's going to happen. Maybe draw it out a little bit on a whiteboard, and then we just kind of followed this one by one, right? This is step 1. We're inserting, so we're always going to make a new node. Then we handle case 0. The size, of course, handles the rest of the cases. Then we handle case 1. Here we handle our case 2. And here we handle our case 3. So overall, I believe this one will work, and we'll check it here in a moment. Why not? Let's do it right now instead. But I do want to do a print, and I wonder if get data at will be good enough. So let's do that. Let's do that. Now let me look at my constructors. Oh, and by the way, I just want to take a quick sidetrack. I learned something from Awful this just the other day, and I never thought about it, but this is a wonderful resource for you guys to consider. Now, I don't know if you've ever thought about making a string out of one character. Now, you might have when you did this assignment, right? Because in the get card, I ask you to return a string which is constructed of 2 characters. Now, there's a few ways to do that, but you probably found that you can't just cout, quotes plus character plus quotes. Because in C++, the double quotes are interpreted as a character array. And so it would say undefined operator for character pointer and char. And, sometimes I want to just say, hey, why can't I use string? I'll type it here in the Google bar. But why can't I just say string char? What's wrong with that? Why can't I do that? Well, if you ever wonder about constructors that are available for classes, you can just search string, class. You can see I already did it there, C++. Go to this reference here, and let's kind of look in here, see what we can find. Ooh, look at this. There's a constructor, and we can click on it. Let's click on it. Let's do C++ 11. And look at all these constructors we have. Look at all these constructors we have. Now, is there any one of these that takes a character, just a single character? This one doesn't. This one definitely doesn't. This one takes a character array. This one takes a character array. Oh, this one takes a char. This one takes a single character, but it takes this int. What is this? What does that mean? Well, let's look at it. That's number 6. So let's go look at number 6. Fills the string with n consecutive copies of character C. So, even I myself learned something this weekend. If I want to make a character, a string out of a character, I'm going to say string, I don't know, Bob. We could put 1 here because I only want it to be length 1. And you put your character in here. G. Now this is yelling at me probably because it's in the wrong place or something of that sense. I didn't include string. Maybe if I do that it will. But that's beside the point. This will compile as long as you get the right stuff going. And I'm sure some of you guys didn't know that. But now you do. See if it compiles down here. See, look at that. It's like, I like that. Alright, enough of my sidetrack. Let's go ahead and do our work here. Let's prove to ourselves that our insert function works and we don't get any seg faults, and I don't see that what print statement, right? So I'm going to make character array or a integer array here. Let's say it's size 6. Well, let's do a fun one here. It doesn't matter. And I just want it to be kind of out of order, right? So let's do maybe a 32, a 64, a 1, a 22, a 947, and I get one more shot at this. Let's do maybe a negative 22. All right, we got 6 elements in there. And the int array size in this case is equal to 6, right? Sibe asks, so will that insert the character at the end only, or can it insert in the beginning of the string? There might be a small misunderstanding here. What this does is, I'll kind of show it to you. S1. So this is a constructor, so it's going to be a brand new, yeah, it's a brand new string. So there isn't already a string that exists. And it's just going to make G. So I'll show you then what the next one does. If you do S2 and you put a 2 here and put a G, it's a constructor. So it will make a GG for good game. Right? And if I really just want to send the point home, if I do a 6 here, then we'll get 1, 2, 3, 4, 5, 6. Does that make sense? So we're kind of like doubling the... I wish that it would just do this, right? I wish that it would just take the G, but it says, hey, this constructor is nothing, so that's all. Maybe I'll leave it there for fun, so you guys can reference it later. Once again, I think awful for that. I looked at that and I said, I've never seen that before. So I'm going to call a constructor. What constructors do I have up here? Well, I've got the sorted DLL, which will be empty. I've got this one that takes an array. And notice that it's calling this insert function already. It's calling this insert function already. So I just don't want you to be confused, right? We're not copying one by one. We're just calling insert. So it should be sorted if we call this. And notice that the copy constructor will also take this inserted array. So we can test them all. But what I would like this one to do is I would like it to take the array, and I would like it to take a size 6. And then we'll do a for int I is equal to 0. I is less than DLL dot. Let's add a getter in here. for the size of that array, I++. Let's go ahead and see out the DLL dot get data at. Get data at I, that's like our bracket operator, and maybe we'll just put a comma here on the side of it to make sure that things work. And we'll see out and then on. So let's go test our results on Bobby here. As you can see, I was testing some programs. So it compiles. Let's give it a shot. We got a seg fault. All right, let's do some debugging. Let's see what happened here. All right, so whenever we do this, the first thing that we need to do is compile with -g. I know you guys don't like Valgrind, but let's see what it says. Let's see what it says. All right, so it's kind of big. It's kind of big because I've zoomed in so much, but we can find it. So look at this. What does this say? Conditional jump or move depends on uninitialized values. What does that mean? Well, it looks like it's seg faulted inside of the insert function. This insert function was called by this constructor, which is taking the array and the int, and this constructor was called by main at line 137. So we can follow the chain here, and I know exactly what happened, but let's just go look at this. This insert function I think is okay. Some of you might go look in here and see where it's seg faulted. It says line 75. Let's go see what that says. Look, here it says this. And it says conditional jump depends on uninitialized values. That must mean that our head is not equal to something. That also must mean our size might not be equal to something. But the thing is, these should be initialized at this point, right? I expect them to. So what does that mean? We got to go up the chain. We're going to go up the chain here. Let's go look in this constructor and make sure things are getting initialized. So what line does that say? That says line 24. Ah, here it is. Here it is. Hey, and guess what? I talked about this last week too, or on Monday. I forgot a initialization here. Now I know this doesn't make much sense, but we need to make sure that that head gets initialized to null pointer before we start calling insert, right? Because we're going to check to see what's going on here. So does that make sense? So this may end up fixing our seg fault. Why would it have seg faulted? Well, let's see what Valgrind says here. On line 85, it says use of uninitialized value, invalid read, blah, 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 process terminating with a sig-sev. That probably means that we dereferenced our uninitialized value, something like that. We somewhere dereferenced something that we weren't supposed to. So if we look at line 85, you'll see here that, look, I dereferenced that. So I ended up dereferencing some uninitialized value, and I think that's where we seg faulted. So, should be fixed now. I hope that was helpful. I know that next year, if I teach this class again, I hope I actually make more mistakes so that I can kind of walk through these debugging things with you guys. I know that a lot of times I'm just so perfect that no errors happen at all, which sometimes is not the case, but I think that's helpful to you guys when I do that. So, did I recompile it? Did I reload it? Let's make sure. And we may have just a seg fault somewhere else, and that's okay. We'll go find it. Yeah, we do have a segfault. All right, time to val grind. So this one should be different. This one should be different. This one says a valid read of size 4 at the insert on line 85, which was called by this function here. This is the same constructor, so it looks like we've got some problem going on here. So I wonder what we can do to fix that. So I'm assuming that when we called our first, let's see where we're looking here. So here we are. So on our first iteration, I'm assuming that we allocated this just fine. All right, we said head is equal to the new element, which means that the new element's next is null and the new element's previous. So now the head knows that it's 1. We also increased the size, so we know that the size is now 1. And then we returned out of here. So then we probably came back up here. And we went into the second loop of this, right? And so now we're going to go insert the next element. So let's follow it. Let's see what happened. It says on line 85, we have a huge problem here. It said invalid read of this. Oh, well, we should not have gotten an invalid read, as far as I know, because up here, we would have put the data inside of the new element, right? And so the head would contain something here, and the new element would contain something here. Now, you guys don't always have the, what's the term I'm looking for? The luxury of checking the notes. I do have luxury of checking some notes. So just so I'm not here for the next 15 minutes, I'll definitely figure out and tell you why it doesn't work, but I just want to check my notes to see if there's anything here that I can see that I've most obviously messed up. So it seems that I do a check to see if the list of the size is greater than or equal to 1. But other than that, the code looks pretty normal here. I don't think this will fix it, but if it happens to fix it... Oh. I don't know. Let's see. If it does fix it, then we're going to have to figure out why it does that. But as far as I know, things will be okay. So that breaks out of the loop, that breaks out of the loop. This will also break out of the loop. This will just exit the program entirely. So let's give it another shot here. I must be making a super silly mistake. I kind of want to val grind it. Yeah, we do get this same segfault here. It's telling me that I have an invalid read of this. Oh, this time it says on line 86. Oh, well, yeah, I know why. That's silly of me. Does anyone have any ideas? Okay, we've got some ideas here. What if the next node is pointed to a null pointer because head is the only element in the DLL? Let's see. You say, could we change the order of the cases? I do believe we could. So that we check for next node is equal to null, pointer first, the third case. Right. But I'm getting an invalid read here on the head. And the only thing that I'm accessing happens to be the new element and the head. So I guess I'm a little confused here because this next node here is not even existing at this point. And it's telling me that this is not okay because I have not... It's like that head is not even alive at the moment or something. Does that make sense, or am I crazy? Hey, let me take a look here. There's got to be something different. Yeah, and so I did that, and then I checked to see if the list is empty. I wonder if our and is messing this up here. Now this is a shot in the dark. Sometimes I take shots in the dark. Because you never know what you might mess up, even if you can't see it yet. Maybe my logic is weird there. Oh, well now we've got an infinite loop. What is going on here? Did I call this in the wrong order? No, that's fine. I mean, I should have put array size here, but... I must not be... let's do this. Let's do some couts. Let's do some couts. Let's see out the item. Let's see out the size of our array. And let's see out what the head might be. I just want to see if it has an address in it. Oh, I wonder if... I think maybe you were right here. Let's see. What if the next node is pointed to a null pointer? Which it might be, right? So we could swap these. But, I mean, that should handle that. Just make sure I got these right. Let's see where we're infiniting. Probably in that while loop, huh? But I don't think we should. Oh, so now we're at the end. Yeah, so I think the while... Look, I think this kind of went well. It looks like we just didn't handle the ending part very well. For some reason, this and size is equal to 0. For some reason, that fixed that. I'll have to come back to that. But it does look like we insert here the 32, the 64. We insert the 1. We insert the 22. We insert the 947. Oh, and then the neg... Oh! And then it gets stuck here on this very last one. And so what does it... Yeah, Yeah, so CBay says that the while loop is supposed to break. But it looks like I've got something wonky here. So it looks like we've kind of found it. So let's see here. So that's fine. And so I say that our current node, let's see here, our current node is equal to the head, and our next node is equal to the head next. And so if the current node and the next node do not equal null pointer, then we'll check this here. We'll say if this is the case. Oh, guys, I'm so silly. Guys, I'm so sorry to take you through this today. I figured it out. How am I progressing this while loop at all? I don't think I'm progressing it at all in any way. Luckily, this delete function we can do in 2 seconds, so I'm glad that we figured this out. All right, that should do it. That should do it. That should do it. Shall we give it a shot? Did we finally do it? Do I run it with Valgrind? Yeah, why not? What? Oh my gosh, guys. Oh, now we've got an invalid read at getDataAdd. Let's just check that. Wow. How did I mess this up so badly? I can't believe it. How did I mess this up so badly? So we fixed this, but now the getDataAdd is a problem. Oh, well, let me see here. How many elements are in here? There's 6 of them, right? The array size will be 6. And so, here's our problem, huh? I wonder if we went too far, or I'm not increasing the size properly. Or no, so look, we did print this, and then I just went one too far. I must have increased the size too much. So in this case, we increased the size, and then we're going to increase the size overall, and that should just return down there. Oh gosh, all right. Let's make that an else if there. Though I don't think so. I'll have to repair this because we do have to move on, and you know, sometimes we all make some mistakes, right? Yeah, so it looks like I'm going one too far there. So I'll have to figure out where that happens. But for the most part, we kind of figured it out. For the most part. And so I'll kind of post that. Let me kind of wave my hands magically at the delete so we can finally just, you know, kind of move on from this. And then I'll post this code. And I'll hang out here for a few extra minutes to try to figure it out. So if you want to hang out with me, you can after I finish this function. Other than that, you're welcome to go. So let me just try to finish up this delete at least, which should be pretty simple. So let me just find it, just so I make sure that I don't mess this one up. So we're going to delete here at some index. in the array. And so I always like to do this check here. Where is it? This one. I always like to do this check here to make sure we're not going to delete anything. We don't have to exit here. We can just return because nothing would have been deleted. And so then all we have to do is iterate through this list and figure out what is going on. So for int I is equal to 0, I is less than the index I++. I need a node traversal node is equal to the head. Let's do a current node and a next node. Next is equal to the next, so we're just going to go through the list here. And then once we found it, we'll be sitting on the current node to be deleted. And so we'll just check for one thing. We will say if the head is equal to the current node, then we will delete the head node. And then we will say that the head is now equal to the next node, size minus minus. Else, the current, else the head is not equal to whatever it is. And so how we'll do that is we will say that the node previous is equal to whatever the current previous is. And so then we will delete the current node, and then we will say that the previous node next equals nxt, and we'll make sure that if next does not equal null pointer, then we will say that the next previous is equal to previous. Size minus minus. All right, so I'm 1 minute over, and so maybe I can kind of just say a few words on it next time. But for now, I'm going to figure out what happened. But this is it for linked lists. Okay, so please come to office hours if you want to talk about linked lists more. I will fix this and upload it. I will also include me fixing it in the YouTube video if you have to go now. But other than that, right now I'm just going to figure out where I messed up my size. So if you're going to get out of here, I hope you have a great weekend. Please let me know if you've got any questions. But if you don't have anything going on, then please... Oh, this is my... Guys, I figured it out. This is not... This is why my whole thing was breaking. This is what... Man, I'm so sorry that I did this to you guys. So I don't want anyone to be confused because the size here should be equal to 0, but that's what happened, is that the size came in here equaling 6. Size was 6, but the head pointer was null. It's because I'm calling insert here. So when I start inserting it, it needs to be 0. That was goofy of me. I knew I was messing up the size somewhere. Oh my gosh. Guys. Okay, everybody, we figured it out. There it is. It's a sorted linked list. Maybe I'll call delete real quick just to make sure it works. Oh, because I want to. But then we can finally move on. Oh, let's delete the second node. Let's delete the 0th node. Man, I hope it works. Oh, no. Please don't do that. Oh my gosh. All right, we deleted the second node, which was 22, and then we deleted the head node, which was negative 22. It all works. It all works. We did it. Thank you all for hanging in there with me. Link lists, we're done. We're finished. For now. And you might have to look at them later, but that's it. So come to office hours if you'd like. Once again, thank you so much for hanging out with me today. Have a great weekend. That's all I got for you.